Right, today we're going to talk analyzing graphs of functions and piecewise functions. This is section 1.7 for you. So we're going to talk about important characteristics of any function, and we're going to analyze the key features. First thing, intervals of increasing, decreasing, and constant behavior. We always read their graphs from left to right. That means we are only dealing with x values when talking increasing, decreasing, and constant. Increasing on a graph, remember it looks like it's going up from left to right. Decreasing left to right will be going down, and constant will be a flat horizontal line. So we'll identify our increasing, decreasing, and constant, and then boundedness and discontinuity will be next. So increasing left to right, well, I see that it's going up right here. I look at my x values. Well, farthest to the left is negative infinity. So increasing, I start at negative infinity, and I stop increasing here when x is 2. Well, negative infinity always gets a parenthesis because we're using interval notation. And the 2, notice here at x equals 2, it's not increasing, it's not decreasing, it's not flat, it's changing. So we're going to use a parenthesis on that end. Then we're going to talk decreasing. Well, going down left to right, that's right here. It starts decreasing at x is 2. It stops decreasing when x is 5. Both parentheses on there because it's changing at those endpoints. And then when is it constant? Remember, constant will be your horizontal. It is constant from 5 on forever to the right, so that's infinity, both with parentheses. Now we're going to talk boundedness. Boundedness is just a top or bottom bound. We're restricted. Well, on the bottom, we're not restricted at all because we go down to negative infinity. But at the top, we can't go above that line. So we are bounded above by the line y equals 3. That's a restriction to our range. And finally, we're going to talk discontinuity. Well, continuous means it continues everywhere. Discontinuous has a hole, a gap, something like that. Well, this function doesn't have any holes or gaps, so it is continuous on all values, so negative infinity to positive infinity. All right, for our next one, where is my function increasing? Well, it's going up from left to right here. It starts increasing when x is negative 2. It never stops increasing, so negative 2 to infinity, both with parentheses. And then we have decreasing. Where is it going down from left to right? It is going down on this part right here. So that's negative infinity until we hit negative 2 for our x value, again with parentheses. And then we talk constant. Well, there's nowhere on this graph where it's constant, so we'll just say none. It doesn't have to have all three features every single time. Next, we'll talk bounded. Well, bounded, on the bottom, I do have a minimum that I never go past. So we're bounded below. By y equals negative 3. We're not bounded above because my arrows go to infinity. And then finally, our discontinuity. Notice right here, when x is negative 2, we have a gap. So we say discontinuous at x equals negative 2, because that's where we have that jump in our graph. All right, for this next one, where is my graph increasing? Well, if I look closely, I'm not increasing anywhere. Then we'll talk decreasing. Well, we're going down for this part of the graph and this part. So we start at negative infinity. until we hit -2. Put that U for or. We start decreasing again here at 3 until positive infinity. We do use the or there because we're not talking about an overlap anywhere. We're saying it's over here or it's over here. I can be talking about either one. And then constant. We're constant right through this section. That is -2 to +3. There we go. Next up, we'll talk boundedness. Well, we're not bounded below because this arrow means it goes down forever. We're not bounded above either, so we'll say unbounded. And then we look for discontinuities. We have 2 of them here, 2 jumps in our graph. We are discontinuous at x equals -2 and at x equals 3 because those are our 2 jumps in the graph. We're also going to talk today about extrema. These are our extremes, our peaks or our valleys, our maximums or our minimums, our tops, bottoms. A relative minima, plural of minimum, is the bottom of a valley. This means it is lower than the points around, but not necessarily the absolute minimum. The relative maxima, same thing, but with a maximum atop of a peak. The absolute minimum is the minimum of the whole function. Nowhere in the function does it go below this. Absolute maxima, nowhere in the function do I go above this. So we're going to determine the location and value of an extrema and classify the type. Well, the first one I see right here is -1, -5. It's a bottom of a valley, so it's a minimum. Notice it's lower than anything else on the graph, so we have an absolute minimum at -1, -5. Then I see, okay, well, I have a peak here. Notice that my graph goes above that, so that's a relative maximum at, what was it, 2, 1. And then I see another valley here. That's a relative minimum because we go lower than it over here at 4, -2. There is no absolute maximum because my graph goes on forever upward. Some people try to say it's infinity, but remember, there's something bigger than infinity. It's infinity plus 1. We can always get bigger than infinity, so we can't say that we have a maximum. Then for boundedness, well, it's not bounded above because there's nowhere that we stop. But we are bounded below. By y equals -5. Notice that if you're bounded below, you'll have an absolute minimum. If you're bounded above, you'll have an absolute maximum. Now let's talk a little bit more about boundedness. Boundedness is just restrictions on the range based on the end behavior of the graph. If you're bounded below, there's some number that is less than or equal to every number in your range. You can determine the lower bound. This graph is bounded below by y equals -2. You're bounded above if some number b that is greater than or equal to every number in the range. You can determine the upper bound. This graph is bounded above by y equals 3. If I just say a function is bounded, then it has a bound above and below. This one is bounded from above and below. And unbounded means there's no upper or lower bound. It goes on to infinity in both directions. We also have even and odd functions. A function is even if f of -x equals f of x. For all x in the domain, the graph of an even function is symmetric with respect to the y-axis. When we say an even function, it does not just mean that it has an even exponent. Some people make that mistake. A function is odd if f of -x equals -f of x for all x in the domain of f. The graph of an odd function is symmetric with respect to the origin. So if I were to graph you an example of these, an even function could look like that. It's reflected over the y-axis. This is y equals x squared. That is an even function. For example of an odd function, I could give you this one. Well, that's y equals x cubed. Notice that I do have an even exponent and an odd exponent on these examples, but that rule does not always necessarily apply because there could be other exponents involved as well. So by inspection, so by looking at the graph, we're going to decide if these are even or odd or neither. Well, my first one here, I can't reflect it over the y-axis, but I do notice that quadrant 1 looks just like quadrant 3. It is reflected about the origin. That is an odd function. Oh, I also have to decide if it's bounded. Well, there's no upper limit, no lower limit, so this one is unbounded. Go. For the second one here, I notice that if I take this right-hand side and I fold it over the y-axis, it's exactly the same, so this function is even. This one has no upper bound because of these arrows, but it is bounded below by y equals -3, because we never go below there. For the next one, y equals f of x here, I notice I'm not reflected over the y-axis or the origin, so this is neither even nor odd. This one is bounded on the top and the bottom, so we say it is bounded. And I like to write down it's bounded above by y equals 2 and below by y equals 0. All right, now we're also going to determine even, odd, or neither algebraically. So remember, if it's even, then f of negative x will equal just f of x. If it's odd, f of negative x will equal negative f of x. So let's plug in negative x. M of negative x equals negative x squared minus the absolute value of negative x plus 1. Well, when I square a negative, it comes out positive. So negative x squared is exactly the same as x squared. Minus, well, the absolute value of a negative comes out positive, so that's just the absolute value of x plus 1. Well, that's exactly the same as my original function. So m of negative x was the same thing as m of x. That means this function is even. For g of x, we're going to try the same thing. We're going to plug in negative x. So g of negative x squared minus 2 times negative x minus 2. Well, negative x squared is the same thing as x squared. Negative 2 times negative x makes positive 2x and a minus 2 on the end. That's clearly not exactly the same as g of x. It's also not g of x with all the signs changed. These two functions are this function is neither even nor odd. And then we have p of x equals negative x to the 5th power plus x to the 3rd power. Let's see what p of negative x is. So plug in negative x. Well, negative x to the 5th power is negative x to the 5th. Double negative makes positive x to the 5th power. Negative x to the 3rd power is still negative, so I have minus x to the 3rd power. Notice that this is exactly the same as p of x, but all the signs are different. So that's when we'd say p of negative x equaled negative p of x. This is an odd function. For continuity, a function is continuous if there are no jumps, gaps, or asymptotes. Remember, asymptotes are those invisible lines that we come very, very close to but never quite touch. This first function is continuous. It is connected everywhere. The second one has a discontinuity at x equals 3 because there's a jump there. And now, how we get these funky functions. A function that is divided into pieces and each piece is defined on a restricted domain is a piecewise function. Essentially, I say, okay, over here, I'm going to follow this function rule. For this section, I'm going to follow a different rule. Over here, I'm going to follow this other rule. So here is my piecewise function. This just means my function's name is f of x. It is all three of these pieces. Let's start with the first part. If x is less than or equal to 0, absolute value of x. So that just means over here, I'm going to graph the absolute value of x. Well, normally it's a V shape, right? But I only care about when x is less than or equal to 0. If x is 0, I get 0. If x is negative 1, I get 1. Negative 2, negative 3, all right. I'm just graphing the left-hand side of the absolute value function. The next section says negative x squared if 0 is less than x is less than or equal to 3. All right, well, negative x squared is our basic parent function parabola, just reflected over the x-axis. So 0, 0, 1, negative 1, 2, negative 4, 3, negative 9, and 3 is where we stop, the closed circle. So there's that function. And then my function is 4 if x is greater than 3. There's 3, 1, 2, 3, 4. Notice it says greater than, so I put an open circle there, and then that's just a horizontal line. Is there any discontinuity? Well, obviously I have a discontinuity there. We say our function is discontinuous at x equals 3. Generally speaking, you should only have to worry about if it's discontinuous at these points where you switch functions. So basically, I just graphed 3 different functions, each on a different section of my graph. Also, make sure, since I'm using markers, that's an open circle. So this is still a function because I didn't have 2 points there. Your assignment will be a worksheet to go with this section.